Hello, good morning student. How are you? What did we learn yesterday? Yesterday we learned about the stereochemistry of Sn2 reaction, and which gives inversion of the stereochemistry. So there we learned how does a nucleophile attack. There are number of possibilities of attack of nucleophile. Number one is a backside attack that we learned, right? Nucleophile approaches from backside to the carbon atom, and there is a departure of leaving group, and the resulting compound is just like the umbrella turning inside out during the high wind. So that type of the thing is called as a inversion of configuration. And second possibility we have learned, that is a front side attack. When the nucleophile approaches from the front side, from the same side of the leaving group, both the leaving group as well as nucleophile has same negatively charged. There is lot of dipole repulsion as well as steric hindrance, and due to this reason the nucleophile approach from the front side is a very remote. So there, that possibility also we have learned. And then third one, other possibility of the nucleophilic attack, or which prove the inversion of configuration. Let us see here what we are going to discuss today. We are discussing the chapter number 3. The name of the chapter is Nucleophilic Substitution at Aliphatic Carbon, and there we are learning the stereochemistry for Sn2 reaction. Here for Sn2 reaction, and there the product obtained is a inversion. In a previous two example, what do we see? We have considered the Sn2 reaction taking place for primary alkyl halide as a substrate, but those substrates are the chiral. You might be heard about, you may be familiar with this word chiral. Chiral means what? The carbon atom to which 4 different groups attach is known as asymmetric carbon atom, or the chiral center. But methyl bromide, it is a chiral, or it is a chiral means there are 3 hydrogen atom are identical, and therefore it is a chiral center. So we cannot prove by considering that example inversion of the configuration for Sn2 reaction. And for that purpose we have written here the experimental proof for inversion of configuration. So here we are going to give the experimental proof for the inversion of configuration for Sn2 reaction. And here the inversion, if you start with, when we start with the chiral center, when we start with the substrate which has a chiral center, then and then we can prove it the inversion of configuration. And for this reason, for the proof for inversion of configuration, we are taking the starting substrate which is chiral in nature. Chiral means then and then we can prove the presence of inversion of configuration. And which example, let us see here is an example. For example, here R minus 2 bromo, R minus 2 bromo, octane, 2 bromo, octane is allowed to react with sodium hydroxide, sodium hydroxide with S configuration gives with sodium hydroxide gives here. Sodium hydroxide gives S plus 2-octanol. So that is one of the suitable example we have considered here. You might be knowing R and S, right? R is it is a Latin word. R means, R we can call it as it is a Latin word rectus, right? Rectus means that it is really, these are the experimental quantities R and S is known as these are the absolute nomenclature system for optically active compound in optical isomer. And as we know that optical activity, what do you mean by the optical activity? Which instrument used to measure the optical activity? Do you know that? Yes, the polarimeter is the instrument used to measure the optical activity of organic compound. And optical activity means what? The substance certain, or the what we can call it as any certain substance dissolve which rotate the plane of polarization through certain angle is known as optical activity. When that compound is optical active in nature, when there is a chiral center is present, and if chiral carbon atoms are present or chiral center is present, chiral center means what? The carbon atom in which it attached the 4 different group is known as chiral carbon. The atom or group of atom carries that carbon atom 4 different group is known as a chiral center. Here R is called as a rectus, means it rotate the plane of polarization to the right side. That optical rotation we are getting, right? That is the stereochemistry. R means that is absolute configuration. S means sinister. Sinister, that is also as a Latin word, and that sinister again means as a left-handed, or levorotatory or the dextrorotatory you might be knowing. If any substance rotate the plane of polarization to the right hand side is known as dextrorotatory and is denoted by small d or minus, and not minus, there is a plus, right? And levorotatory means what? If any substance rotate the plane of polarization to the left hand side is known as, or is said to be, levorotatory and denoted by small l or negative charge, like this. So where that plus and minus, so that is related to as a experimental quantity, and R and S configuration, it is again depending upon the what we can call it as a sequence rule, or it is known as a CIP rule, right? CIP rule, CIP, and the CIP rule, or it is known as sequence rule, CIP rule, or which is known as a sequence rule. And according to that rule, the priority groups are arranged around the chiral center is known as the sequence rule or the CIP rule. CIP, these are the scientist names. C indicate as a Kahn, E for Ingold, and R for Prelog. These three scientists studied this thing together and putting the one precise rules formulated, and that's why it is called as the CIP rule or the sequence rule. What are the point? What are the rule? There are near about 4 points are there. First one is the atomic number. That is the first rule. Those atoms having the atomic number greater, they should get the first priority. Second rule is known that is depending upon the next atom. If two atoms are the same, then you think about the next atom. Third one, that is about the double bond or triple bond. So suppose C double bond O, so C connected to 2 oxygen atom like this, triple bond, carbon nitrogen triple bond are there. Then that carbon connected with 3 nitrogen atom like this, and the fourth one which is known as isotopes, right? Isotopes, and as we know that isotopes means what? Having same atomic number but different mass number are known as isotope. For example, hydrogen has 3 isotopes. Which are those? First one is a hydrogen, second one deuterium, and third one is a tritium. All are having as a 1 atomic number, but their mass number, hydrogen has 1, deuterium has 2, and tritium has 3. So likewise this is a rule, and according to that rule we can assign or give the correct IOP configuration of this compound, right? Now here can you draw the structure of this R minus you indicate as a, here is a levorotatory 2-bromo-octane. And now here the structure, and as we know that structure we are going to draw here on the basis of Wedge formula, because we are learning the mechanism. And now here 2-bromo-octane. Let us see octane. Octane means what? 4 carbon. No, there are the 8 carbon atom in the straight chain. 1, 2, 3, 4, 5, 6, 7 and 8, right? Octane means what? This is a oct indicate as a 8 carbon atom in the straight chain. A and E, there will be a no double bond, and therefore this is a straight chain. Now look at 2 position. You number from this side or this side, doesn't matter, but here 2 to indicate as a position of bromine atom here, and therefore I am putting 2 at this position, right? And now as we know that rest of the thing you connect the hydrogen atom. Look at here, this carbon atom has 1, 2, 3 bond. How many hydrogen atom I should attach here? 1, right? Very good. Here is a 1 hydrogen atom. Now look at, this is a terminal carbon atom, and terminal carbon atom always containing only 1 bond is there, and therefore you should attack 3 hydrogen atom here. This carbon atom, 1 bond is here, 1 bond is here. Therefore, how many hydrogen atom I should attach here? I am attaching 2. Here again 2, CH2. Here again CH2. Here CH2. Here CH2, and here CH3. Likewise, so this is the structure of 2-bromo-octane. Now R means what? The plane of polarization rotating the clockwise manner. This type of the you have to arrange that a group around that carbon atom on the basis of the CIP rule or the sequence rule, and then we can call it this is a R configuration, and if opposite, this one is called as a S configuration. R and S are the absolute configuration. Now first of all, tell me, observe this structure carefully, tell me how many chiral centers are present in this compound. This is the name of 2-bromo-octane. How many chiral centers are present? Look at here. Only 1 chiral carbon atom is present, and it is denoted by asterisk or it is a star here. Only 1 carbon. Look at here. This carbon atom carries 4 different groups. 1 hydrogen, 1 is this group, another one is this group, and this way. Means there are the 4 different groups are there, and therefore this carbon atom is a chiral center according to as a font of 2 raised to n is the number of isomer you are going to get. But let's see here, only 1 chiral center is there, and here 2 hydrogen atom, and therefore it is a chiral. Remember, most of the students get confused, achiral and the chiral. Chiral means what? If you talk about only 1 chiral center is present, and this 1, 2, 3, 4, 5, 6 and 7 are the achiral carbon atoms are. Achiral atom, more than 2 atoms are similar attached to that carbon is known as a achiral, and chiral means 4 different groups attached to, or the carbon carries the 4 different group is known as a asymmetric carbon atom or the chiral center. Understood this one? Now let us draw this structure in a R form. Look at here, I am trying to draw here R, Br. Br is a living group as we know that, and 1 methyl group I am writing here CH3. This methyl group carbon atom and Br I am showing by the normal line. It clearly indicates that these 3 atoms are present in the same plane. They are lying in the same plane. Now I am showing another bond by dotted line. I am putting here hydrogen atom, and now I am here, look at here, this hydrogen, methyl group and bromine, 3 I am writing here, right? And this carbon atom I am shown by star or asterisk, and now the rest of the thing collectively you can draw here, 1, 2, 3, 4, 5 and 6. There are 6 carbon atoms are there, and that's why I am writing here condensed formula, we can call it as here C6. 1, 2, 3, 4, 5 and 6 carbon atoms are there, therefore C6. Now how many hydrogen atom? Count and tell me. Here 2, 2, 2, 2, 2, 10, and these 3 are 13, and therefore you can write here C6H13, right? This is the structure of R. Why it is R now? Look at, there are the 4 different groups are there. Now according to as a first rule, sequence rule, depending upon the atomic number. Now tell me, here is a carbon atom, here carbon atom, hydrogen and bromine. Which atom has a highest atomic number? Bromine atom. As we know that halogen family member, fluorine, chlorine, bromine, iodine, these are frequently occurring in the organic compound. You should remember the atomic number of those halogen atom: fluorine 9, chlorine 17, bromine 35, and iodine I think 127. These are the atomic numbers are there, and therefore is 35. Therefore among these 4, this atom has highest atomic number. It should get the first priority. It is getting first priority. Now tell me, among these 2, here is a carbon atom, this bond is attached to carbon. Which carbon atom? You go, here is a carbon, here is also as a carbon. Then apply the second rule. What is that second rule? Next atom. Next atom, if you see here, this is a carbon. Next atom means another carbon atom. 2 hydrogen and 1 carbon. Here are only as a 3 hydrogen atom, and therefore it will get the second priority, right? This is a second priority, and third priority will be this one. And look at fourth priority of this carbon atom. Now while showing as a RRS configuration, you travel from 1, 2 to 3. Look at here. This is a 1, 2, 2, 3. Look at what type of the rotation it is. It is a clockwise rotation. And fourth priority, which goes below the plane or above the plane, that remains as it is, and therefore this is a R configuration, and that's why the name of this compound is R, and minus is a Leo rotatory R 2-bromo-octane. So this is the name of this compound, and now this compound further treated with aqueous sodium hydroxide by Sn2 mechanism. What in a Sn2 reaction, we know that it is a concerted reaction, one step reaction. Nucleophile is prefer to approach from the back side, and therefore here OH minus is approaching from the back side, and there is a departure of leaving group, and we are getting here the transition state formed over here like this. This is a HO, then this bond is going to form, and whereas this leaving group or the bond between carbon and bromine is going to break, and this is the hydrogen atom, and this is one of the hexyl group like this C6H13, and one methyl group which is over here, and this is called as transition state. This is a transition state, and as we know that this is a rate determining step. Rate determining step means what? We can measure the actual rate, how much time is required for the conversion of reaction into product, and this one is a fast step. In the second step is a fast step. Fast step, within the fraction of second reaction takes place, and we are getting the formation of the product over here HO, then C. Look at here, this methyl group is over here, the hydrogen atom is here, and this group is the hydrogen atom I am showing here, hydrogen atom here, and this the hexyl group C6H13 as it is. This is again is a chiral center, and there will be a Br minus. Now find out what type of the configuration it has. Again, give the priority number. This is a carbon atom, chiral carbon atom. Here oxygen, here carbon, and this oxygen atom is having atomic number 8, and therefore it will get the first priority. Then among these two methyl group, as we know, it will get the second priority, and methyl group should get the third priority. This one is a fourth, but you travel first 1, 2, 3. You first observe 1, 2, 3 only. Don't think about as a fourth one while showing as arrow. Look at here. This is a completely counterclockwise manner, means anti-clockwise direction, and therefore, and look at the fourth priority which is below the plane, and therefore this type of the configuration is termed as S configuration. Yes, and then at 2 position 2 octanol, OL indicate as a alcohol group is there, and therefore look at here, and in this way we have proved the inversion of configuration in the Sn2 mechanism. We started with the chiral substrate, and we got our chiral substrate has R configuration. When experimentally, when it is putting in the polarimeter, the result, this is rotating the plane of polarization is exactly opposite to the starting compound. The optical rotation is on a right hand side. When the product measured, then it shows the optical activity on a left hand side. Means this is a S configuration. This clearly proves that there is a inversion of configuration present in the Sn2 mechanism. This is what we can call it as experimental proof for the inversion of configuration. But here, we cannot give the evidence, because our starting substrate is a different one and the end product are different one, and therefore they may show the optical rotation is maybe different due to the different product form, and therefore we are going to learn the second evidence for inversion of configuration. I think let us stop today here. Remaining we will see the next time. Thank you. Have a nice day.